Okay, we're just about to start the session 7. Yep, in a few seconds. So welcome to the session 7, the surveillance session. I'm just calling right now the first speaker of the session, Alexander Mustin from the University of Salford in the UK. Is Alexander around? Oh, here he is, sorry. Okay, so you're welcome to join the stage. And Alexander is going to talk about targeting surveillance for Xylella fastidiosa in Europe, an epidemiological basis of this activity. So, Alexander, the stage is yours.
Okay, so good morning, everyone. Thanks for all coming out to listen to me today. My name's Alex. I work at the University of Salford in the UK, and I'm going to present some work today we've done with Frank van den Bosch at Salford, at Stephen Parnell at Salford, and Johan Burris at Rothamsted Research, looking at how we can use epidemiological models to inform surveillance strategies for Xylella in areas where the pathogen is not yet thought to be present. Okay, and my talk focuses on these four main questions. Firstly, I discuss the issue of surveillance aims, so basically why we're conducting surveillance in the first place. Given a lot of surveillance is focused on visual inspection of plants for signs of disease, I'll then talk a little bit about Xylella's lengthy asymptomatic period and the impact that can have on surveillance when we're using visual inspection. And then I'll talk a little bit about two possible ways to get around some of those problems. Firstly, looking at using different tests in host, and then secondly, looking at actually testing vectors instead. Okay, so to start off, it's good when we're looking at surveillance to really consider what are our surveillance aims. Why are we doing surveillance? And we can look at that in two general ways. We can look at it in terms of what our knowledge of the pathogen is in the system that we're looking at. So do we think it's present? So in this case, are we trying to control it? Are we trying to measure how prevalent it is? Or do we think it's absent? In which case, has it been recently removed? Has it possibly been recently introduced? And so I'm going to focus on these issues where we think that the pathogen is absent today. And we can broadly divide our surveillance approaches into these two general questions of early detection surveillance or absence sampling. And these basically differ in terms of these two questions. So for early detection surveillance, we're interested in how bad the situation is when we first detect it. For absence sampling, we're looking at how bad could it be given that we've not detected it. And our previous work over the last few years, we've developed methods where we can actually quantify and answer these questions in a useful way using formulae such as this one. So this formula represents the answer to this question: how bad is it when we first detect it? And given that we know a little bit about the epidemiological characteristics of our pathogen, a little bit about our surveillance plan, a little bit about our diagnostic plan, we can actually quantify what our maximum prevalence at first detection would be. And we can also do this using a different equation for this question of how bad it is, given that we don't detect it. Okay, so I'm going to talk a little bit about the asymptomatic period of Xylella and how that impacts on surveillance. These are some models created by Johan at Rothamsted, looking at the spread of Xylella in a series of different plots. And we can see different colours here. So the red is infected with symptoms, the kind of light green is infected with no symptoms, so the asymptomatic ones, and the dark green are the uninfected. And as you can see, as it spreads through from a completely uninfected field, the majority of early infections are infected but are not showing symptoms. So these are the cryptic infections that you won't be able to detect using visual inspection. So taking one single snapshot, so we can see in this field, that we've got a few symptomatic hosts, but the vast majority of the field is infected, and the vast majority are asymptomatic hosts. So using visual inspection, we won't be able to detect those. Oops. And even worse, when we do detect it using visual inspection, the situation will actually be much worse than we think it is based on the prevalence of visual signs. So using our methods, we can actually look at how those two quantities relate to each other. So we can plot these on graphs. So looking on the x-axis, we can look at the apparent prevalence, so the prevalence of hosts with visual signs of disease. And this obviously, this axis goes up to about 15%. And on the y-axis here, we can look at the true prevalence of infection. And our formula allow us to look at how these two kind of relate to each other. So and we looked at this for a few different pathogens. If you look at this paper here by Vasti Alonso Chavez, where she looked at the impact of asymptomatic period for detection. She looked at a few different pathogens, including Phytophthora ramorum, which spreads relatively slowly and only has a very short asymptomatic period. And as you can see, for Phytophthora ramorum, at a prevalence of about 15%, as an apparent prevalence of about 15%, the true prevalence is also about 15%. So there's not very much of a difference. Looking at it for a variety of other pathogens, if that works, we can see that the pattern is quite different. And at the time, we looked at Huanglongbing, which obviously had been spreading in Florida, has got a long asymptomatic period and relatively rapid growth rate. And we found that actually it was much, much worse. So it's apparent prevalence of about 15% with Huanglongbing. Your true prevalence is over 75%. So that makes it very difficult to catch it at an early stage. Using data from Juan Naves Cortez and some surveillance data, we've been able to look at spread parameters for Xylella, especially the quick decline syndrome in Apulia, and we find it's actually even worse. We've also looked at estimating an asymptomatic period using previously published data, as Stephen mentioned before, as part of the EFSA update of the pest risk assessment, and it's described in the poster out in the hall. And we basically worked out that the asymptomatic period for Xylella is somewhere in the region, on average, of about 313 days. So we've got about a year asymptomatic period, a rapid growth rate, and we find that Xylella then works out even worse than Huanglongbing. So it's about 15% prevalence, where over kind of 80% of cases will be infected. So what impact does that have on our surveillance approaches, and what can we do about it? Using our methods again, we can therefore look at the impact of different detection lags on the maximum prevalence at the time we first find infection, as we show here on the y-axis. And we assume for this we're going to fix a sampling rate. So I used some of the data from Apulia and estimated kind of the rough sampling rate in the buffer zone there. And we found out that on average they're sampling around 840 trees per day over a kind of a short period. Now I imagine that we might want to detect it before we reach a certain prevalence. So taking this prevalence of 0.4, which is based on Gianni Gioli's model yesterday, which suggests you may be able to eradicate at that kind of point. But this is just an illustrative example. So imagine we want to detect by that point. If we've got a detection lag of 313 days, you can see that we exceed our prevalence at the time of first detection, given that we're sampling with that intensity. So what can we do about that? One thing we can do is to increase our sampling intensity. And that will shift that whole curve right down. Now, in this case, we'd have to increase it about 5-fold. So we'd have to be sampling about 4,000 trees per day over that kind of short 50-day surveillance period, which is unlikely to be practical. Another option is that we can keep that current sampling rate and just try to shorten that detection lag. So we can't use visual inspection. So instead, if we maybe consider a diagnostic test that can detect earlier, to reach our threshold prevalence, we'd have to be able to detect reliably at around 6 months. Now, that's potentially possible. It's difficult kind of getting a reliable diagnostic in asymptomatic hosts, but this suggests that there is some potential for diagnostic tests in hosts to improve our surveillance strategies. Are there other alternatives? I've decided to have a look at vector testing, which has been mentioned a little bit over the conferences the last day or so. And I've looked at it before. So I looked in this study at how we can use epidemiological models, linked models of host and vector infection to work out where we should target surveillance if we want to basically get the best bang for our buck, so the best chance of detection early on. Now this model assumes that both host and vector prevalence increase in line with each other. Now that's not really the case for Xylella, because we have this very seasonal pattern of infection in vectors where all vectors are uninfected when they first emerge, and then they rapidly become infected, and then the infection kind of declines as the population levels drop. So we created a new model which allows us to answer this same question, which links together the host prevalence and the vector prevalence, and then we use data from these 3 papers on the seasonal vector abundance, the prevalence of infection in vectors, and we also use surveillance data from the same areas covered in these studies to measure the prevalence in olive hosts during that time. And we use that to fit this model, and I'll present the results from that now, if this advances. Okay, so our model basically, it's a mathematical model. It has components of differential equation models and difference equation models. We model the infectious prevalence in hosts, which we're going to assume for now is equal broadly to the prevalence of visual signs. As Dan Chapman presented yesterday, these two are correlated with each other. So infectious hosts are more infectious, symptomatic hosts are more infectious. And we assume that it broadly doesn't change per year because we've got this long asymptomatic period that will buffer out any kind of fluctuations over the year. So we have each year a fixed host prevalence which increases over time as the epidemic proceeds, as you'd expect. And then we use a differential equation model to model the vector prevalence over time on a daily basis, accounting for the fact that vectors emerge and will then spread the infection. So we can see we get these peaks of infection as the infection spreads. We can clearly see from this model that early on in the infection, the prevalence in vectors, so shown here in blue, is higher than the prevalence in hosts during that peak kind of time when vectors are around and they're basically on olives in kind of early summer. So that would suggest to us that focusing your surveillance on vectors will give you a better chance of sampling infected vectors at any single time point. And given that your diagnostic methods are the same, so they're able to detect with the same reliability, and they'll have the same costs, that actually that would suggest that focusing on vectors would be your best plan. Of course, tests aren't the same, so I've looked quickly at what is the impact on the varying the sensitivity of your vector test, assuming that our host test is broadly known. So assuming that we've got it's of cost about €550 per tree to conduct visual inspection and confirmatory ELISA and PCR. At what ranges of host diagnostic performance would it be better to use vector testing than host testing? And using some provisional results from the LAMP test, which we worked out costs around €13 per insect. Basically, we'd have to have a diagnostic sensitivity, so a probability of correctly identifying infected vectors of around 0.6 or so, for that to then be a useful alternative to visual inspection. Okay, so we're running out of time, so I'll just quickly summarize what we've found. So basically, surveillance for Xylella is complicated by the long asymptomatic period and the rapid spread rate. Although visual inspection may still be useful for other surveillance aims, especially when the pathogen is more established in the population. In order to account for that, we'd need high surveillance efforts, and the viability of those surveillance efforts will depend on how early they can detect, their ability to detect infection, and their cost. Our results from the model suggest that testing vectors will actually give us a better chance of detecting than detecting in hosts, because the vector prevalence is much higher early in the epidemic. Okay, I'd like to thank everyone involved in this, and a lot of people who've provided us with data, especially data on vector testing, as well as obviously the X Factors project and the Bridget Consortium, which I'm a part of as well. Thank you all for listening.
Thank you. Thank you very much, Alexander, for the presentation. So we've got time for at least a couple of questions. Does anyone have a question? Yeah, here, Walker, on the back left of the room. Here comes the microphone.
Thank you very much. Wopke van der Werf, Wageningen University. Thanks very much for that. Can you give us an intuition, an insight, why it is that the incidence of Xylella in the vectors is higher than in the plants early in the season, not later in the season? Is it because of multiple visits, or what is it?
So basically, why do we have the lag before infection, the prevalence increases?
Yeah, and especially why is the vector prevalence higher than the host prevalence early on?
Yeah, so the way I see it is that basically the vectors, the adult vectors, obviously are the mechanism by which it's spread, the pathogen is spread. There's only a very short period of time they're actually part of that pathosystem when they're moving around from host to host. So they have to firstly be on the olive hosts, which in Apulia at least seems to happen kind of early summer. And then the density of vectors drops off quite severely as time goes on. So there's a very short period of time where they're able to spread. So because we can see that Xylella spreads so quickly in olive groves, there must be a high prevalence in vectors to maintain that kind of rapid rate of spread. If they weren't becoming heavily infected, if there wasn't a high prevalence of infection in vectors, then I would expect the spread would be much, much slower. So this might be a characteristic kind of particular to Xylella, but it definitely fits according to our parameterization of the model, which was obviously based on the data that we had available.
And would you like validation data for this?
I would, yes. So we've tried our best with the data we have basically taken from the literature. As has been pointed out a few times by Dan and by Stephen as well before, the surveillance data we have that we're relying on for the very, very important host prevalence estimates is biased because they had a very particular surveillance aim of delimiting infection, finding out how far it had gone, and they would generally go to areas and focus intensively on certain areas where the prevalence may be different. So we found it very difficult to infer exactly what the true prevalence would be in those particular study areas based on the surveillance data we have. So as has been pointed out a few times over the conference, that getting unbiased data on host prevalence and also kind of more data on vector prevalence would be really, really useful. And then we could refine this model and kind of really categorically work out whether it would be a useful approach to test vectors.
Okay, we've got time for an additional question here. Okay, first here in the front, and then last question just behind.
Yes, thank you for this presentation. I had a question. It is about the early detection. So I can imagine that this model is applicable in an area where the pest is already established, and we want to follow the front line of an infection. But in a new introduction scenario, where it might come through a plant or one single event not linked to a vector, I don't think you will have so much chances to capture the right insect unless you have such big sampling effort in that whole area that you have to cover.
Yeah, I think if you had a single infected host, then you'd have a hard time finding an infected vector, but equally you'd have a very hard time finding that infected host as well. So basically, we find that overall the surveillance effort would still suggest that we should be focusing more on sampling those vectors, because once it starts to spread, and it is that initial exponential growth where we're getting a rapid relative increase in the prevalence, then we would expect to start to see that prevalence earlier in the vectors, even when it's very, very low, because the alternative is to have absolutely massive surveillance focuses on the host. And as we've shown, that the visual inspection really, it doesn't work. There's a 1 year asymptomatic period. With that kind of duration of asymptomatic period, it's going to be really tricky to actually detect anything. And then using diagnostic tests is also going to be tricky because you need to make sure you sample the infected tissue on the infected host. So I think even though it will still be difficult, the earlier you want to try and catch it, and our models allow us to work out exactly how much surveillance effort you'd need, it still would be better to focus it in vectors.
Okay, we move to a short
Thank
last
you very
question.
much. Nandor Petais from the European Commission. My question relates to exactly the same issue. Okay, if you test the vectors and the result is negative, everything is okay, and you can assume that with a high level of confidence that the Xylella is not present in the area. But if you catch positive vectors, what could be the proposed follow-up measures? What kind of surveillance on the plants you need to detect the level of incidence in an area?
Yeah, that's a really good question, and that's something that we'd probably have to work with risk managers and people more experienced with control strategies and things like that. So we'd suggest that you start off by working out exactly how confident you want to be, what your maximum acceptable prevalence would be, and then you base your control measures on that. So it's kind of a two-way dialogue between the planning and then the subsequent control. It's a very good question in terms of literally what do you do when you first detect, and it's a good question that is true for if you're testing hosts as well as if you're testing vectors. If you first detect a host, our methods can tell you what we would expect the true prevalence in hosts to be at that point, and our methods from the vector sampling can also tell us, if you detect it in vectors, what the expected true prevalence in hosts would be. But literally how far you have to look in terms of a spatial pattern, we're looking into that now in terms of can we link up some kind of spatial model to work out a distance that you would go to try to control or contain an infection. But it's a very good point and a very pertinent point.
Okay, thank you. Thank you very much again. Just before we move to the second talk of the session, I have to inform you that we are expected to be at exactly 1 p.m. in front of the main entrance door of the building for the picture, the photograph concerning the meeting. So please keep in mind that at 1 p.m. sharp, we are supposed to be at the main entrance of the building for the picture, for the photograph of the meeting. Thank you very much. Okay, so it's time now to welcome the second speaker of the session, Arturo Hornero from the Swansea University. So please, Arturo, the stage is yours. Sorry. And Arturo will present us the results he obtained about the spatiotemporal monitoring of Xylella in olive trees using both RTM and S2 images. So Arturo, please.
Well, thank you very much, Philippe. Morning. Let me introduce myself. I'm a second-year PhD student in physical geography at Swansea University in the UK. My main interest is focused on the most recent developments in remote sensing. My current research is based on the quantitative estimation of vegetation dynamics using high-resolution hyperspectral data, medium-resolution satellite imagery, and radiative transfer modeling. In the last years, we have focused our applications or efforts in monitoring Xylella fastidiosa in different parts of Europe. For instance, in a recent publication in Nature Plants, this publication was also mentioned several times during the previous sessions. We show how using high-resolution hyperspectral and thermal images can reveal Xylella fastidiosa infection in olive trees before symptoms are visible. However, Xylella fastidiosa infections have spread rapidly through Europe, and it is clear we need to develop models at the global scale. Thanks to the current satellite imagery, we can assess vegetation trends globally. Sentinel, in particular, Sentinel-2 is the current satellite freely available with the highest spatial resolution, up to 10 meters. Well, it depends on the bands we are focused on, but vary from 10 to 60 meters per pixel, with a high revisit frequency of 5 days at the equator, which means even higher revisit time at higher or lower latitudes. And this is done in 13 spectral bands, covering from the visible to the SWIR part of the spectrum. This is a great example of a Sentinel-2 scene versus hyperspectral images over the olive orchards. As we can see, working with satellite imagery, we have lower spatial resolution. So the spectral information of the different components are aggregated in gigapixels. This implies the needs for using physical models to transfer information across different scales in order to retrieve biophysical properties of the vegetation cover. As we can see in the bottom scheme, there are different components included in a 3D radiative transfer model, so we can retrieve the biochemical composition and the structure of the canopy from a satellite image. So I would like to present a new methodology for monitoring Xylella fastidiosa infection from space. This study, which was recently accepted and should be published in a few weeks, evaluates the use of Sentinel-2 images together with a radiative transfer approach to control epidemics caused by Xylella fastidiosa in olive trees. A 2-year time series of Sentinel-2 images was used to describe the temporal dynamics of olive groves infected with Xylella fastidiosa. And also, for its validation, visual measurements were made in the field together with high-resolution hyperspectral images taken from an aircraft. So regarding the table of content, first we'll have a look at the study area and the data collected. Then we will review the image analysis performed, the different approach in modeling, as well as the result obtained and the conclusions we have reached. So this study was carried out in an olive grove in Apulia in southern Italy. We were talking a lot during the previous session about this location. In this location, Xylella fastidiosa was officially detected for the first time in October 2013. We conducted the field surveys in 16 olive orchards located in the area infected with Xylella. The disease severity and its incidence were evaluated in more than 3,300 trees. So based on visual inspection, we assigned to each tree one of the 5 severity categories available. This is the same severities we were using for the Peter Berg work, but we were using MODIS in that research work. These severity categories vary depending on the proportion of the canopy affected by the typical symptoms of Xylella fastidiosa. The severity varied from 0, which indicates the absence of symptoms, to 4, when most of the crown branches were dead. The incidence, in contrast, only consider whether a tree is affected or not, which indicates symptomatic and non-symptomatic trees. The first campaign was held in summer 2016, and we observed that 50% of the tree had no symptoms. When the survey was repeated in the next summer, this value was only 15%. In order to study this temporal variation, we introduced a new concept, a new term, the relative increase in Xylella infection, and we express it as delta DS and delta DI for the increment for disease severity and disease incidence, respectively. So here, values greater than 0 for delta DS and delta DI imply an aggravation of visual symptoms. 0 value correspond to orchard with no significant changes, and values below 0 indicates a decrease in visible symptoms, which never happened in our case, in our study. Important to say, the data collection was partially supported by grant agreement Ponte and X Factor under Horizon 2020 from the European Union, and it was made possible thanks to project leaders Donato Boscia, Blanca Landa, and Juan Antonio Navas. So regarding data, airborne collected data, we used the Sentinel-2 data during the first 2 full years after its launch in 2015 to build a multi-temporal spectral data set. We corrected the images atmospherically, and a mask was also applied to filter the clouds. We selected vegetation indices compatible with the Sentinel-2 spectral bands, so conventional indices in the red and near infrared, such as NDVI, MSR, or GNDVI, adjusted indices such as AT-SAVI, RV, or O-SAVI, and other formulations sensitive to the chlorophyll content for the sweet part of the spectrum. Finally, a smoothing algorithm was used to reduce the atmospheric variability and to fill the gaps to produce a daily time series of the indices. Following the same procedure we did with the incidence and severity for each orchard, we calculated the temporal variation of the vegetation indices. So finally, and then we established a Pearson correlation analysis to compare them with the increase in incidence and severity. For validation purpose, we collect very high resolution hyperspectral images up to 40 centimeters per pixel. And this also allows us to evaluate the contribution of the background in the temporal variation of severity and incidence. Regarding the model simulation analysis, we use a couple model to analyze the sensitivity of the different indices. We were also using this model to evaluate the effect of the background on the detection of symptoms. The prospect leaf model was used in combination with a 3D flight canopy model to simulate the heterogeneity in the different orchards. We built a lookup table with more than 7,000 simulations, which was classified in the different levels of severity and incidence. So to define the variation from one year to another, we established a set of combinations to describe the increase in the severity and in the incidence rate. So we proposed 3 different strategies that were raised to take into account the background. On one side, a more sophisticated solution, which includes the variation for each orchard individually. We call it temporal background per plot, TBP. More straightforward approach, on the other side, considering that there is no change in the background, persistent background, PB, and a compromise alternative where we calculate the spectral average of the background of all the plots together and their variation. We name it as mean temporal background, NTB. So finally, we evaluate, following each of the approach, the estimation of delta DS and delta DI with Sentinel-2. The results demonstrate that in order to carry out infection monitoring from Sentinel-2, the use of self-corrected vegetation indices and radiative transfer modeling is needed. So vegetation indices that minimize the atmospheric and the background effects, such as RV, AT-SAVI, or O-SAVI, obtain better results than the traditional ones, like NDVI or MSR. Also, the indices RV and O-SAVI produce the highest coefficient of determination with delta DI, also with delta DS, with an R-square of 0.75 and 0.76 respectively, with a p-value below 0.001. Surprisingly, and this is something we can see on the bottom right figure, this is something we were struggling a lot from the beginning because it's contrary to what might be expected. The higher incident increased values, the delta DI, were associated with smaller reductions in vegetation indices. This was finally also demonstrated with the model simulation analysis. This was due to the effect of the background on the signal and the temporal variation. So model simulations field observations show that the background effects have a significant impact on the temporal variation of the incidence level. With the different strategies proposed, we found that the use of radiative transfer models improved the estimates by 25% when the background effects are taken into account, and by 32% when the heterogeneity was also considered. This is an excellent example of this. how the application of this methodology with OSABI and the MTB approach, with modeling, the compromise solution, applied to a complete Sentinel-2 scene, allow us to generate a map of the expected increase in incidence between 2016 and the following year. To conclude, Sentinel-2 demonstrates that this data enables the detection of changes associated with temporal variation of Xylella fastidiosa-induced symptoms at orchard level. It's partially same conclusions we reach from the other work working with MODIS, but among the vegetation indices used, the best performance was observed for those that minimize the atmospheric and background effect, such as RB, OSABI, or AT-SABI. And these vegetation indices perform better than the traditional ones. However, the confounding effects of the background had an enormous impact on the vegetation, on the vegetation indices obtained from the image. This study demonstrates that the 3D radiative transfer modeling and field observations properly explain the temporal variation experienced by both the tree canopy and the background. This is a critical aspect to accurately predict delta DS and delta DI. So we could say that the proposed methodology can provide useful spatiotemporal indicators to track the damage caused by Xylella fastidiosa infections in large areas. That's all. Thank you very much for your attention.
Thank you very much. You're right in time. Okay, we've got time for one question, maybe two, not sure, at least one question. Yes?
Thank you very much. Can you hear me? Yeah. Yep. My question is how applicable these methodologies to other areas? Do you always need validation from field observation with inspectors going to the fields, or is already at the stage in which you can just combining satellite imaging and aircraft images, you already can have a good proxy of these the temporal increase or decrease in infectivity, etc.?
Yeah, this is a quite interesting question. In a way, how can we apply this model approach to other areas? So the first thing to come to my mind is, do we need to use the data we were using from the beginning? The answer is no. We can start with satellite images and some measurements for the ground, just for an initial assessment, but then we can apply the same methodology for other areas. So feel free to propose any collaboration. I'm free to and open to collaborate with any other groups.
Okay, thank you. Thank you very much again. We're moving to the next speaker. It will be possible, of course, to continue the discussion during
we want to continue the discussion
no
there.
problem. We are now welcoming the next speaker, Elena Lazaro Hervas, from the Instituto Valenciano de Investigaciones Agrarias in Valencia. So Elena is going to talk to us about the optimization of the delimiting service strategies for Xylella fastidiosa in the demarcated area in Alicante. Back to Alicante then. Okay, the floor is yours.
Thank you very much. Good morning for everyone. I will start my presentation with the background of how the limiting survey strategy is specified in the current legislation and how is the situation in Alicante demarcated area. Well, according to the decision in which Xylella fastidiosa measure I specify, the limiting survey must cover an extent of at least 5 kilometers surrounding the infected zone. This area must be split in two zones according to different epidemiological units size definition. The first kilometer must be split in a 0.01 kilometers square grid size, and the rest of the zone must be split in 1 kilometer square grid size. Visual inspection of all the epidemiological units is compulsory, and only sampling of symptomatic plants and asymptomatics are on. This is a graphical description of how the delimiting survey strategy is specified in the current legislation. Here's some information about the Alicante demarcated area. The first detection and demarcation was announced on July 2017, and our work is focused only in the 2018 official delimiting survey inspections and only results up to January 2019. This is considered our reference database. Here, some metrics about how the official inspection was carried out in relation to the number of hectares surveyed, the number of insected zones, the number of cells of the different epidemiological unit size, and the number of samples taken. This is a graphical description of how the distribution of the different epidemiological units, and also this is a graphical description of the samples distribution. In green color, negative samples to the presence to Xylella fastidiosa, and in red color, positive samples. This is, these photos shows almond trees that is the most frequent host plant in which Xylella fastidiosa has been detected in Alicante demarcated area, and only just to show the most typical symptomatology related to the leaves and the general aspect of a tree affected by Xylella fastidiosa. Our work follows a twofold objective. The first one is to develop an alternative delimiting survey because we want to optimize inspection and sampling intensity. And just for now, I am going to focus in explaining some of the methodological aspects that we have taken into consideration in order to develop this strategy. We want to improve the efficiency and keep the efficacy of the current one, the current one delimiting strategy by optimizing inspection intensity and also sampling intensity. Inspection intensity is defined as the number of cells to be inspected, and sampling intensity is defined as the number of samples to be taken in a specific cell. We propose, or our proposal is a sequential adaptive strategy. Sequential because we want to organize in different time frames the survey in the different resolutions, size that are going to use to define the different epidemiological units. And our proposal is adaptive because we want to tailor the inspection and sampling intensity for each survey resolution depending on the previous observed values. Under the same methodological approach, we propose two designs, a three-phase designs in which 3 resolution sizes are considered in order to define epidemiological unit size, and a two-phase designs in which 2 resolution sizes are considered to define the size of the epidemiological units. This is a graphical description. As a toy example of our, in order to show our alternative delimiting survey. As you can observe, the number of cells to be inspected in the final resolutions depends on the positive cells that we have found in the previous one. So also we have the interest to estimate an optimum value to the sampling intensity for the different resolutions that we have into consideration to define epidemiological unit size. So we are going to propose an optimization algorithm to estimate these sampling intensity values. Survey effort described as the total samples that we have to take in all the delimiting survey is computed using this generic formula in which sampling intensity and inspection intensity is taken into account. This slide shows the scheme of the optimization algorithm that we are going to implement in order to find an optimum sampling intensity value for its resolution site. Well, I will try to explain in an easy way. We start with an initial value of the sampling intensity, and we run 100 random sampling configuration according to restriction that is imposed by the sampling intensity initial value. And only if the 50% of the replicates identify the reference positive cells found in our reference database, this sampling intensity is considered as the optimum value. Here, some results in relation to inspection intensity, that is to say the number of cells to be inspected, that are estimated for our 3-phase and 2-phase design in comparison with the inspection intensity related to the current legislation. As you can observe, in that table and in this graphical description of the three scenarios, our proposals improve the efficiency of the current strategy in relation to the inspection intensity related to the 0.01 kilometers squares grid size. Sampling intensity, that is to say the number of samples to be taken in a specific cell, for the 3-phase and the 2-phase design are estimated using the optimization algorithm that I have explained before. For the 3-phase strategy, in 51 samples per cell to the 1 kilometers grid size, into 45 samples per cell in the 0.25 kilometers grid size, and in 14 samples per cell in relation to the 0.01 kilometer size. In relation to the 2-phase strategy, the sampling intensity, the optimum sampling intensity estimated for the 1 kilometers grid size is coincident with the 3-phase output, and the sampling intensity estimated for the 0.01 kilometers squares is estimated around 15 samples per cell. This table shows the survey effort computed taking into consideration also inspection intensity outputs and sampling intensity outputs, is estimated for the 3-phase and the 2-phase design, taking into consideration inspection intensity and sampling intensity optimus obtained by the application of the optimization algorithm. As you can observe, the sequential adaptive strategy in both designs improves decrease the survey effort in comparison with the current description of the limiting survey strategy. We also have another objective in order to validate the assessment, the performance of our alternative delimiting survey in relation to sampling intensity. We want to assess the effect of sampling intensity in incidence estimates. Sampling intensity is an output that we have obtained by the application of our delimiting strategy. An incidence, defined as the proportion of infected plants per 1 kilometer square cell, it could be a derived quantity important from an epidemiological point of view, because it can give us the information about the abundance of Xylella disease in Alicante demarcated area. So our proposal is to compare incidence estimates with the reference database, that is to say the data that belongs to the official inspection of 2018, with different data subsets created limiting the maximum sampling intensity value. Data subsets have been created limiting sampling intensity according to a reference value. The reference value that we have used are 9 samples per cell, 23 samples per cell, 37 samples per cell, and 51 samples per cell. Remember that this output is this output is coincident with the sampling the sampling intensity value that we have obtained by the application of our optimization algorithm. So we want to simulate data subset has been creating, simulating 100 replicates for each data subset according to a random sampling scheme in order to guarantee a correct exploration of sampling space. Incidence, described as the proportion of infected plants in a 1 kilometer square cell, is modeled using a Bayesian, Bayesian hierarchical spatial model, and we want to explain incidence using information of some climatic covariates and a spatial structure effect and a random effect. After a model selection process based on the reference database feed and using 2 scores criteria, we have selected this model because he explains in a better way the incidence estimates in Alicante demarcated area in order to carry out the comparison that we have to run. Here, just to show only results in relation to the comparison with the reference database and the data subsets estimates in relation to the mean of the posterior distribution of the incidence. We have compute bias at the subtraction between the incidence of the reference database and an average incidence of the subsets database. So only to remark that data 51, in which sampling intensity value has been fixed in 51 samples per cells, seems to show the lowest bias value related to the all epidemiological units that define our demarcated area, and this bias value are very close to 0. So this sampling intensity value seems to be a good reference value to give information in 1 kilometer's resolution. Also to show a comparison with the reference database and the data subsets in relation to a standard deviation of the posterior distribution of the incidence. This is an uncertainty measure of the incidence estimates. And also the results are coincident with the other one, and the bias related to data subset 51 shows the better results. Only just for concluding, in relation to our alternative delimiting strategy in Alicante demarcated area, this strategy, sequence inspection and sampling in time considering different spatial resolution size, so it could be a logistically more feasible strategy than the other one. It also as delimit the extension of the disease in a larger space resolutions while demarcated infected area in finer resolutions, and also improves inspection intensity at the 0.01 kilometers square grid size, here some metrics that I have shown before, and also the alternative delimiting strategy reaches an improvement of survey efforts. Also, in relation to the assessment of the performance of the limiting strategy, our proposal finds an optimum sampling intensity value for 1 kilometer resolutions that seems to be an adequate reference value. That's all. Thank you very much for hearing me, and also thanks Regional Health Plan Services for providing us the database. to exploit them, and also here all the projects that support financially this work.
Thank you very much. Okay, we are pretty well on time again. Thank you very much for that. We've got time for a few questions. Is there any question in the audience? Okay, just to stimulate the interactions. I was wondering, did you interact at some stage, either at the regional or national or even European level with the risk manager about the conclusions of your work in terms of perspective concerning the evolution of the management of the situation by next year?
Yeah, I have so these outputs. I have shared these outputs with regional health. Sorry. Okay. I have shared these results with regional health plan services, and also I am involved in some work with EFSA. So I think this is a specific delimiting strategy alternative adapted to the situation of Alicante Demarcated area. I think that is not the only one that has been applied. In fact, EFSA is working on in this work, and the EFSA is also working on developing different strategies to account this specific type of survey. So yes, I have shared these outputs, but I think that this is not the only possibility to perform.
Okay. But although it is not such a generic situation, no, at least it is a very detailed contribution, I think, to the
Yes, I think that survey inspection intensity strategy, it could be exported, but the estimation of the sampling intensity values are dependent of our database. So, for instance, if I is providing some statistical methodological support in order to estimate sample size calculation. So I think that it is possible to combine those one.
Okay, thank you. Any other question? No? Okay, thank you very much again. It's time now to welcome the last speaker of the session, Cbins. Cbins Vos from the Alpha Unit EFSA in Parma, Italy. And Cbins will present us the EFSA Toolkit for Xylella fastidiosa risk-based surveillance in the EU member states. Okay, are you all right?
Yeah, I'm okay. I have the light just in my eyes because the other speakers were like this. It's okay.
Maybe it's possible to.
Okay, good morning. Yes, so I'm Cbins Vos. I'm working in EFSA, and I'm going to present to you the ongoing work on the development of a toolkit for Xylella fastidiosa risk-based surveillance in the EU. So let me see, like this. Okay, so very briefly, we were told not to talk about regulation, but I have to explain the regulatory context in which we are doing this work. We are doing this work for preventing better the pest introductions, for better risk targeting, and for working with more statistics to have a better representation of the different surveillance phenomena. So the first point is in the legislative framework is the PLH regulation 652/2014 that is about the co-financing of the member states for capacity building also of surveillance in the member state. And we have the new plant health law that indicates across different articles the different types of surveillance that are required. Some articles are dedicated to the surveillance in areas where the pest is not known to be present, and other articles are addressing the surveillance in protected zones of the European Union, and the other ones on the surveillance in demarcated and infested zones. Also, we are working in the context of international standards for phytosanitary measures, and there we have a whole series of them, and we have some very technical ISPMs, in particular the ISPM 6 and the ISPM 31, that are giving guidelines, international guidelines on surveillance and on sampling consignments. And then we have a whole series of ISPMs that are more procedural ISPMs that help to better apply this surveillance in different contexts. Across this international situation and the plant health regulation, we have the distinction, we have to acknowledge the distinction of 3 different types of surveys. We have detection surveys, delimiting surveys, and monitoring surveys. And in this context, we have received a mandate by the European Commission and to facilitate the member states with in their planning and execution of the survey activities to provide practical and concise outputs to the member states to addressing all the pests that are in the work program 2018-2020 for surveillance of quarantine organisms, and to provide, in particular, guidelines for surveillance of 3 pilot organisms. So, to address this mandate, we thought we cannot do that in one single document. We have to sort of develop a toolkit to assist the member states in this work. The first element of the toolkit are pest survey cards, and we are developing pest survey cards for more than 50 pests that are in the work program of the member states, and Xylella fastidiosa, of course, is one of them. We are also delivering survey guidelines. This work is still, it's still ongoing work, it's progressing. And we have 2 types of guidelines. We have general guidelines that will address the general, in general, the organisms. And then we have specific guidelines that we are developing for Xylella fastidiosa, Agrilus planipennis, and Philosticta citricarpa as pilot organisms. And the third tool of this toolkit is the support that we provide to the member states in the form of workshops, where we are facilitating the member states with the use of some statistical tools for making informed calculation of sample sizes for their surveillance. And we try to help them in tailoring this work to their own situations and to make a statistically and risk-based survey design. The pest survey card for Xylella fastidiosa has been already published, is available on EFSA website, and this pest survey card, the objective basically of it is to provide the key information and the guidance that is necessary to collect, to gather the information that is relevant for performing surveillance that is risk-based and statistically based. And to do that, there are data requirements for performing pest freedom surveys, and these data requirements are, in fact, the basis of all the toolkit that we are developing. The first element that is important to consider is the target population, and we have had a lot of presentation during this conference about the host and Xylella interactions. But what we need to do, we need to ensure when we are going to make a survey design, we need to make sure that we target the right host range and the host plants in the right areas. So we need to have a good knowledge of this target population a priori before designing a survey. And we need to have the information about its size and its structure. So in addition, we need to characterize better the landscape in terms of target population and try to divide it into homogeneous spatial units, units where the epidemiology would be similar in terms of interactions between the host, the pest, and its environment. Another important element is for applying a risk-based approach is for optimal targeting of the survey, we need to have an information in the landscape and in the introduction, in the spread of the disease, etc., that can help us to assess the areas, the actions, the activities, and so on that can help us to better target this surveillance. And we need to provide an estimation of the relative risk of these different elements. Without a relative risk estimation, we cannot go for risk-based approaches if we want to do it on a statistical basis. Another very important element is the detection and the diagnostic methods. And here we have to understand well for each one of the survey cards and for each one of the pests that we are addressing, what are the different components of this detection and diagnostic methods, all the way from the field, from the natural environment where the target population is, to the laboratory. So we are dealing from the sampling procedures all the way to the testing in the laboratory. And the key element here that we need to characterize is the sensitivity of the overall method. So it is not only the test sensitivity in the laboratory that is interesting for us, it is also to know how we make the right choice of the sample in the tree. How do we have a good sampling procedure that can, in fact, pick out of the tree a positive leaf when the tree is positive? And then a very important component of all this statistical approach is to have a clear definition of what is the level of acceptability of the risk. This is something that we cannot address. That is something that is somehow defined as the goal of the surveillance. The risk manager community has to agree on these elements. So how confident do I want to be to measure the pest at a certain level? That is somehow going to be the major input that is needed from the risk management community to be able to run a statistically based survey. So what do we need to look for? First of all, in the surveillance for Xylella fastidiosa, and we described all these different processes in the survey card, as I've already indicated. We are looking for any type of Xylella fastidiosa subspecies in terms of STs, etc. We want to find any type of Xylella fastidiosa in different environments. We have already here a map that was shown before where we see the different area where the pest is now being found in Europe, but also we have a world distribution. And we need to find any type of Xylella that can interact on our territory. And we have had the clear presentation that these different combinations of pests with specific environments develop different epidemics. So what we need to find is any sign of any new epidemics. That's the objective of a detection survey. So the target population, where, what are the hosts that we want to target with our surveillance? Here it is a very complex exercise. It's a very polyphagous bacterium, as it was already mentioned throughout this conference. And we have a good inventory of the host plants in our EFSA database, and in the 2018 version, we had listed 563 host plant species that were extracted from the scientific literature, from which 312 were confirmed by at least 2 molecular tests, and from which 192 were shown to be infected under natural conditions. So what we suggested in the survey card is to focus on this 192 host species. And what we need to understand how these host species are being articulated in the environment. And we thought that to have a better understanding of the environment, we should maybe reduce it and divide it in 4 host plant categories. The ones that are agricultural hosts, the ones that are growing in semi-natural areas or natural areas, we have the ornamentals, and we have also the forestry. So already these 192 host species can be divided in 4 different groups. Then ongoing work that we are doing is about the ranking of host plant genera. So from the different surveillance activities that were performed in the EU, we have received the data of their surveillance and the monitoring. And what we have done with this, what we are trying to do with this, is to derive the probability of infection of a host genera. And this would help in a detection survey to better target the survey. We are also trying to define the probability of the infection in the different regions, because that would help to better target the survey within the demarcated areas, in particular within the buffer zones of the demarcated areas. And the third element that we are trying to, that we are preparing is the calculation of the probability of symptomatic plants to be infected. And this would also help a lot in a more informed choice of the host plants to survey within demarcated areas. This is all ongoing work, and we expect all this work to be finalized before the end of the mandate. And of course, we are going to have a first presentation of the outputs in the end of November to the member states. Risk-based surveys. This also addresses the question of where should I survey. So here, apart from the the informed choice of hosts that can show symptoms where the probability of infection could be higher, we also need to consider the spread, for example, and other elements. So how did we define a risk factor? We defined it as a biotic or abiotic factor that can increase the probability of infection by the pest in an area. So, in fact, we somehow propose a procedure where we start by the identification of the risk activities that take place in the area to survey. And these risk activities could include the trade, the movement, the imports, the preparation of plant propagation material, etc. And from a sort of how do you say that, selection of the higher risk activities, we could then link them to risk locations, where we could be more precise, indicating the areas that really matter for the surveillance of the Xylella fastidiosa. And around these risk locations, we could use the information and the knowledge we have about the spread to somehow delimit the areas around where we have more chances to find Xylella after it has been introduced. And these spread distances are based on the different modeling exercises that have been presented in the PRA, in the EFSA updated PRA. And so we have somehow extracted from this modeling exercise, short distance spread of the disease, some key distances that help us to design the risk areas. We also have some information about the median of short distance dispersal that has been indicated in the pest risk assessment, where there are some key values that we are using for developing our strategy, or a strategy for informing the surveillance based on the risk. And I'm already out of time, okay? So I will try to go quite quickly around this. Okay. So risk-based detection surveys, we have some posters that were hanging with more detailed information. And if you have not had the time to look at them, I invite you to go and have a look at them. So this image shows a target population, and within this target population, we can divide some epidemiological units. And in the middle, we have a risk location that we have identified according to the procedure that was explained before. And around this risk location, we have to define what is the risk area. So this risk area we can consider for a detection survey is 150 meters, because that would be the median, according to the PRA, fitted to the Apulian data. And the idea being to detect the pest, if it is present, 150 meters being the median is sufficient because the infections are persistent in the host. Once we have found it, the situation will be different. Then we go to the delimiting survey. So upon a positive finding, we initiate a delimiting survey for defining the infected zone, and we will demarcate it after with a buffer zone. So after a positive finding, the first step is to link this finding to a source of the infection, and around this source of the infection, we are now going to trace the different rings for the demarcation and for the delimitation. And these rings, they are also depending on the number of years since we have performed the last detection survey in the area. And we use then the spread capacity of the disease that has been modeled in the PRA. The third step will be to survey in peripheral bands around this source of the infection, and whenever a peripheral band of 400 meters of the year, the maximum range of the spread of the disease, once it is free, then we go to an inner band. So we do a concentric, we do the demarcation, delimitation in concentric bands from the periphery to the inside. If we find it, then we have delimited the area with the most external band. Okay. About the detection and the identification, a lot of discussions have been we have had during this conference, and in fact, the visual examination should not be completely excluded. In particular, it is very important to increase the effectiveness of the sampling. And the visual examination in particular is important when we are in the demarcated area. What I said before in the beginning of the talk is that what is very important is to combine the operations in the field with the operations in the lab. So to have a clear idea of how good our method is from the field to the lab, and not only focus on the lab. The next steps, we have some workshops that we have organized to provide these simulations and to work with the member states on simulating their own situations. And after these workshops, we want to gather their feedback and finalize our different guidelines documents for Xylella fastidiosa. I want to thank in this all this work that we are doing now for 2 years, the different colleagues from EFSA, the colleagues from the EFSA PLH panel, the external experts, in particular Elena Lazzaro, that is here also working on the host probability of finding a host infected, and tasking grants, so the collaboration with member states, with different organizations of member states that are working with us on this activity. Voilà.
Okay,
Sorry,
thank you very much. Thank you very much, Cbins. Right, since we are a little bit running out of time, I suggest that some specific questions for your presentation arise later on, just right now, during the general discussion.
Yes,
no,
yes, you will recognize me, just feel free to ask me.
Okay. Okay, thank you very much again. I will now, thank you. I will now invite all the speakers of the session to get back on stage for the general discussion. Okay, please take a seat. Have a drink if you need. Okay, so it's now to the audience to ask some additional questions to any of the speakers or to several of them at the same time. Yes, Giuseppe, just here in the front.
Thank you. So I would like to ask the fourth speaker to talk about the model for risk-based surveillance, how this system can be combined. How do you see a possible integration between epidemiological surveillance, risk-based statistics, the experience in Alicante, the satellite detection? Do you see a possible integration in the near future of all these methodologies for Xylella surveillance?
Well, my opinion, I think that we should make an effort to work together, combining all the solutions. I fully agree with you. I don't know the answer yet, of course, but hopefully we can work together looking for the same solution. It doesn't matter if at the end we use high-resolution satellite images, modeling approach, mathematical approaches, or whatever. The final goal, of course, is giving us an idea how to proceed from one side, monitoring for the other side, eradicating the disease. As I said, I'm free to help anyone with their approach to try to combine, makes together an affordable solution.
Any additional comments? Yes, Siren?
Yes. We are not working in isolation. It's very important that we cannot work in isolation, and we are using the same models. We are converging on the use of the different outputs that come out of this type of conference, and we work together directly, indirectly. So all this output that is coming in accordance of all the work that is ongoing also.
Yes?
Yes, I'm Pasquale Di Rubba from the European Commission, the Plant Health Unit. Just a simple question to the panel. Since we have seen several strategies for sampling, for monitoring that have been explored by the different presentations, are there any assessment carried out on cost? So whether we go in one direction, what could be the benefit, but what could be also the cost involved? So is this cost economic dimension has been further explored by the different panelists? Thank you.
Yeah, and cost is a really, really important issue, especially for early detection surveillance, absent sampling, where you've got to maintain it for indefinite periods of time. And there's been a lot of work looking at the costs in relation to the costs of control. So, for example, optimizing your strategy, which I've personally talked about optimizing in previous conferences. But there's also ways that we can tweak our methods to explicitly incorporate the costs of just surveillance per se. So you can treat that separately and look at the overall costs of a different surveillance strategy regardless of the actual control strategy at the end. And I think probably the best way is going to be to consider both those ways of incorporating costs. Because quantifying the cost of a complete control strategy or the cost of an incursion that isn't managed, I imagine there's a lot of variation and uncertainty in that. So it'd be a case of breaking it down and trying to explain it in intuitive ways.
If I may add, we have heard from previous presentation that surveillance is very cheap if you compare it to what would happen after in terms of impact, etc. So I don't think that the cost is the main issue. What we want to know if the surveillance is really able to address our common objective of protecting the territory, protecting a production sector. So maybe the problem should be turned around. How much would it cost to protect correctly a sector? And then we see how far we are from it with the available resources.
Well, as you both said, the cost of these modeling solutions is too low in comparison with other approaches. In the case of using free satellite images, of course, they are free. On one side, we have not the highest resolution, but enough spectral information for feed the models. On the other side, of course, we need to carry out several surveys from the beginning to as an initial assessment, because in the model I was presenting, we need to have an initial assessment, because this is monitoring and how the increase of the incidence and severity over the years. So you need, of course, an initial assessment, but the cost in comparison with other solutions is lower.
Okay. Any other point you'd like to interact about? Yes?
Thank you. David Demarcated from INRA, France. Yeah, just to add on this point of the cost and the benefits of a surveillance strategy, I think that we're seeing more and more proposal speaking about adaptive strategies for surveillance. And a nice way in which we should hierarchically order those strategies should be one, for me, one idea is to go from the cheaper to the more expensive. So first maybe a remote sensing, and then once you have detection, then move to another and have a kind of list of which one goes first, that is, should be the cheapest, and going down towards the last one should be the lab analysis, in which that really takes cost and time of a researcher and technicians. And so for me, the question now is, what should be a good metric for evaluating a surveillance strategy? Where should we put the mark on this is a good strategy, this is the right way of doing? What is for you the challenge of that?
I think the first important parameter that we need to consider is if our system is able to detect the pest at a level that we can still do something about it. That the design prevalence of our method is sufficiently low that we can still eradicate the pest if we find it. So that is the early detection, the definition of the early detection. So it should be tailored to each pest, but that makes it also very complex. But I think the essential parameter to consider is, yeah, when you find it, can you still do something about it?
Yeah, I mean, I suppose expanding on that point, it's like I mentioned at the start of my talk, that we need to really be focused on what exactly is your surveillance aim, because your whole approach to surveillance will vary. So I've talked about targeting surveillance, Cbins talked about targeting surveillance as well towards particular high-risk groups. So that's really useful for early detection surveillance, but it's not as useful if you want to estimate an overall prevalence. And like I mentioned with the problems we've had with the actual surveillance data I've been using for parameterizing my models, sometimes it's really, really useful just to know what is the prevalence in an area, in which case, obviously the best approach would be random sampling, or maybe there's some other strategies, stratified sampling and things that might be more economically justifiable. But always tie whatever you're doing into a particular surveillance aim or objective based on the state of the pathogen in your system, and then, like Cbins said, you evaluate in terms of how well that surveillance aim is then being met. And there's probably probabilistic ways you could do it. You could do it in a dichotomous way as well. But definitely, yeah, attributing some kind of level of confidence is always going to be really important to your results.
We had another question here in the center of the room.
Yeah, my name's Mike Robinson, Animal and Plant Health Agency, UK. This is a question really about production of almond trees in Israel. Obviously, I understand that there's an increase in production in Israel of almond trees. Is that correct? Also, in terms of propagation and production of the trees, is this entirely self-contained within Israel, or do you import propagation material?
Okay, so indeed the almond industry has been rising in recent years, although I think in the past maybe couple of years there hasn't been a significant increase, but it had increased in the last decade quite a lot. As for the seedling production, so they're all manufactured in Israel. We don't import any plant material from outside Israel. So rootstocks are coming from tissue cultures, and all the science are coming from local orchards.
Thank you.
Okay.
Hello, I'm Alex Obradovic from Serbia. I would like to congratulate to all panelists for their contribution. And I have a question for Ofia. From the dots representing the infected plants, it seemed to me that the incidence of the disease was pretty high. And pictures that you showed of the trees show that those are pretty old trees. Have you been able to estimate how old is this infection?
Yes, so I think the pictures, that, especially the satellite pictures with the red dots, are a bit misleading because the dots are much bigger than a single tree, but they still represent just one single tree, while on the satellite they may cover like maybe 6, 7, or maybe 10 trees altogether. So the incidence is what I showed you. It ranges between 3 to 7% of the total trees in the most infected area. As for the age of the orchards, so the majority of the orchards there were planted somewhere between 2005 to 2010. So they will be somewhere between 9 to 15, 16, 15 years.
Yes, but you know, when you see such a big tree affected seriously, do you speculate when infection took place?
We can try to speculate. I think the people from Italy and Alicante are asking exactly the same question. I heard some people saying that the initial infection may have occurred, you know, tens of years earlier. So we can't really say about that. We do have some data about how long it takes for the symptoms to appear when you do mechanical inoculation or graft inoculation in quarantine facilities, but in nature, if these trees were actually infected by insects and very few insects, it seems it's really difficult for us to estimate when exactly the initial infection occurred and what was the source as well.
So planting material was mostly originating from Israel, and no neighboring countries reporting the outbreak of Xylella. Where did it come from? What do you think?
Well, it's a good point. So first, you know, no neighboring countries reporting Xylella doesn't mean the neighboring countries doesn't have Xylella, first. And secondly, what we can say, well, at least based on the sequence type that we have in Israel, that it's probably originated, well, originally from somewhere in the United States, but we don't know how it arrived to Israel, whether it arrived with infected plant material from the United States or maybe from somewhere closer to Israel by other means, such as the vectors that we so far haven't been able to found.
Thank you very much.
Okay, we've got time for an additional couple of questions before getting to the front door of the building for the photograph, for the picture. Yes, Antonio?
So, Antonio Vicen from IDEA. My question is for the panel, but also maybe people in the room can follow up on that. If I remember the talk of Cbins, there are two components. One is the sensitivity of the detection method, usually what we do in the lab, but the other component is the sampling efficiency or effectiveness. I have Francis Peter just in front of me, so we are improving a lot the part of the lab, so sensitivities now are very, very high, but not sure we are improving in the same level the sampling effectiveness. This is linked with visual inspection and the training of the inspector. So do you see any way of formalize somehow the improvement of this part, because at the end is the bottleneck of the whole system. If you don't take the proper sample at the proper time, maybe then you get in the lab a negative result.
Yes, it is. I agree with you. This is really the bottleneck of the system. If we have overall method sensitivity that is very low, we will have to take a lot of samples to be able to find the pest. So it can be improved, like you said, by training, but also by a sort of harmonization of sampling procedures if we want to compare on specific crops, if we want to be able to compare method sensitivity from one survey to another. So we need to sort of benchmark, I don't know how you say that, we need to sort of define some minimum levels of sensitivity for different effectiveness of sampling for different crops by running some exercises on testing sampling procedures. I think it has to be done maybe in the first step in experimental settings, and then it could go further using the data of the surveillance and to measure, confirm and validate the values. But it's a sort of a bottle in the ocean that we are throwing with a nice message in it. So we need somebody to pick it up. Yeah.
And just on a related point to that, when I was going through kind of preparing parameters and things for my presentation, we looked into this very issue about host sampling and host testing. And we had a lot of trouble getting estimates of exactly how early you can detect infection. What is that kind of detection lag, basically, when you're using a laboratory test for hosts? Because a lot of the studies are really, they follow over time, but they take different samples at different locations from the inoculation site. And it's then we found it very difficult to interpret exactly a kind of estimate for an overall host from that. So I guess we need to consider, yeah, getting some of those parameters out of, getting data on those parameters.
Just one additional element. It's not only that part. Also, we need more, maybe more information, maybe a ranking of the performance of the different laboratory tests, because we have a lot of inventories of laboratory tests, but we don't have a very clear best method that is recommended for each situation. That would be fantastic if we can provide this to the persons in the different labs that do the testing, because everybody might go in different directions.
Okay. Last question, maybe? It seemed to me there was somebody here on the right. No? Yeah. Okay. Last question. Thank you.
Okay. My question is mainly for the first speaker, Alexander. When doing surveillance in a non-infected zone, if you identify a first infection, you must be more than reasonably sure that this identification is really reliable. And I'm afraid that if you address the Xylella identification on vectors, vectors might be not the best target because of few reasons. Besides the fact that they host a very low bacterial load, and using standard methods, this can provide some problems. But the major pitfall is that you cannot resample insects, unlike plants. Even if you GPS the collection site, once you have made the detection on a insect sample, then you cannot go back and resample. And while you can do that for plants, if you GPS the plant. So I agree with you that you can obtain some hints, and you can maybe go back to the precise site to resample for plants, but I'm afraid that in previously non-infected zone, you cannot only rely on vectors. That's my complaint.
Okay, just a short comment about that?
Yeah, it's a very, very good point. Obviously, my model is non-spatial, so it doesn't account for kind of spatial issues. And like you said, you could have vectors that move in and maybe aren't transmitting and issues like that. So I think that, yeah, if you get maybe useful for absence sampling. So obviously you're talking about what do you do if you detect it in vectors, and then it relates to the question I got before. So yeah, maybe we need to look further into that response and what would you do? Where would you sample? Where would you look? I think there would possibly be a suggestion to look further in hosts, but then what do you do if you don't find it in hosts? But yeah, it's a very important question that we'd have to consider.
Okay, thank you very much. That's it. That's the end of the session 7, so the surveillance session. So thank you.